Good morning, everybody. My name's Ghadi Shayban. I'm very happy to be here today. This is, like has been said before, this is one of my favorite events. I'm usually not able to make it in person. I usually end up sitting on YouTube, mashing the refresh button, waiting for the videos to get released at the end of the summer. But I'm glad to be here in the flesh today. It is pretty rare to have a group like this one assembled, people who develop, evolve, and maintain something like the Java ecosystem over long periods of time, successfully, I might add. That's a rarity these days. I work for Cognitect. We consult, we design systems, we coach. We do this across a lot of different industries. Cognitect also stewards the Clojure programming language, the subject of today's talk. We have a database, Datomic. It's a high-performance relational database with a pretty unique approach, which was the subject of a talk at a previous summit, a talk given by Rich Hickey, the creator and designer of both Clojure and Datomic. But before we get rolling, it's customary to mention a few legalities here. Things I'm going to discuss are intended to start a conversation. They are not commitments, roadmaps, casual promises. So, with that, why Clojure? Clojure is about problems. It's about solving problems. It can solve the problems at hand. It can position you to solve future problems. It's not going to solve future problems, but it helps you sleep well. It is integrated with the Java platform. It's not an island that has a bridge to the platform. It's designed to get leverage with the vast majority of mature libraries and facilities that that are already existing on in the Java ecosystem. So another dimension to problem solving is information processing. We all do it. We all deal with information in our various fields. Information in the form of maps, associative data structures, sequential things, lists, vectors, sets, transformations of those data structures. Clojure is designed around information and data. It's designed to let you learn how to manipulate this information once, not to learn a little micro DSL for every little API you're dealing with. Like, I mean, how many people have to remember, is it get line item or just line item or something else? It's all these little micro DSLs everywhere, but it's really all about information processing. So you learn how to manipulate the information once, and that pays off because the data is the interface to everything. Clojure gives you side effects when you need them because your programs do need them. You need to do things in the world. You have to effect change. So Clojure programs are usually situated in the world where you perceive things, you decide how to act, and then you act or react to things. Notice one thing I didn't mention is cool VM technology or cool compiler technology. That's not what Clojure is about. It's mostly about solving problems and processing data. So, and that's pretty humbling. Today, we're going to look at how the language maps itself into the lower level constructs, how they map into bytecode, how constructs become bytecode, and challenges that are particular to Clojure. But I figured we'd start off with a little taste of one of the libraries in Clojure called clojure.spec. What is it? It is a specification system for data structures. So in Clojure, you're usually dealing with maps, sets, lists, scalars, very generic data, but your particular needs are always specific. So you want to actually say something specific about what is in this particular map. And clojure.spec is a specification system for data structures. So as an example, if you had a fulfillment system, you might receive a map as a request, but it contains an order payload or a parcel ID, stuff like that. So if you're going to go to the trouble of specifying a data structure, you want to get as much reuse and leverage for the effort that you put forth to specify something. And so we'll look at what leverage looks like in a moment. But clojure.spec is just a library. It doesn't have any hooks into the compiler. It is totally user space. So as an example, most of the time you're going to be wanting to match maps, but let's take a look at matching sequences instead. This is the definition of one single spec, a spec named myjvmls/spec. The S prefix to people who don't read Clojure is it's a namespace alias, so S is the library for spec aliased here. So this defines a spec as the catenation of two other specs, and those specs are something has to match a keyword, and then there needs to be a series of numbers that match. And so this is, in effect, a regular expression over a sequence. Normally, regular expressions are over characters, but this is over just an arbitrary sequence. Okay, great. What can I do with that? Well, you can check if a particular sequence matches the spec. And so here we're calling, we're applying the spec as a validator function to some input. Does the input conference 2019-728 match? Yes, it does. It returns true. Great. But wouldn't that be nice if it returned you more than one bit of information? Well, you can say, how does it match, rather than whether it matches. So here we're saying, conform the spec against this input. And so what it does is it acts as a parser, in effect. So it will match the first part of the spec, the keyword conference, and then it will match all the numbers following, and it'll sort of pluck them out of the input, just like capturing works in regular expressions. It just sort of destructures them. Great. What if something doesn't match? There's a keyword oops at the end that causes the predicate to fail. All right, you're still looking for more than one bit, right? You want to know how did it fail. So you can ask it to explain how it failed, and this gives you back a plain data structure that contains the problems encountered trying to match. And so here it finds one problem, and it says that the predicate number wasn't satisfied by the value oops, so it tells you how it failed, it tells you where it failed, it says at index 3. It also tells you how the index within the spec. Sometimes specs can be nested, they can have branching or alternation, so it'll tell you how it failed along the spec path, not the input path. But anyway, this is really rich information that you can feed into a pretty printer, tools, IDEs, and you can visualize this information in interesting ways. All right, so here I'm gonna start to feel like an infomercial host, but there's more, all right? You can take the same predicative matcher and you can turn it inside out. Instead of recognizing data, you can use it to generate data. Notice it doesn't describe how to generate data, but specs that match lists, maps, predicates, they know how to derive generators from themselves. And so you get really, really nice capabilities for testing. This is super useful for fuzzing. If you have an API, you can generate request maps and just slam an API with a bunch of things. So this is a really great facility. And so you can see the leverage you get for describing one spec. You get validation, you get conformance, you get data structure generation. You get a whole bunch of other things that I don't have time to cover, but that's the sort of leverage that we want to get with Clojure. We want to get maximum leverage for the effort applied. And so this is leverage on libraries, this is tooling, platform. That's where it's sort of situated. All right, spec's cool. It's worthy of a whole workshop, but let's look at how the language works. It's a Lisp. So you have a REPL, it's a standard REPL. It reads data structures off of a source. And so you get maps, lists, vectors. And then you want to macro expand all of the macros that are encountered. So it just does that until it hits a fixed point, and then it feeds that data structure into the compiler with eval. Usually there's some sort of class loading involved where it emits a class and loads it immediately. The compiler is a one-pass translator. It goes direct to bytecode. There's not much optimization. It's not to say that Clojure isn't optimized, it's really carefully put together, but the compiler doesn't really do massive transformations of user input. So how do specific elements of compilation map into bytecode? Well, let's take a look at most of the elements. We have literals that appear in source code. We have ways to call things. We have ways to capture closures. We have the data structures that are the workhorses of the applications. And then we have a namespace system where we can bind function implementations and give them names and give sets of those names as well. So the easiest one to look at is scalar values. This is not a comprehensive list, but the mapping is really, really straightforward. You generally need to invoke some sort of constructor. It's worth noting that depending on context, numbers can be emitted unboxed or boxed. They're unboxed if they're feeding into a context where they're needing to be used in an unboxed scenario. So if you write along and you're calling a Java method that needs a primitive long, it's going to emit it unboxed. But for the most part, constant literals are going to get stuffed into static fields and put on the stack when they're needed. All right, collections. These are super frequently used. They all map in a very similar way. You're going to make an array, you're going to populate the array with the elements of the collection, and then you're going to invoke some sort of constructor that's appropriate for the collection. They all work in the same way. Vectors have arity specialized constructors that take the arguments in an already spread form, not in the array. I will call your attention to the map example. The first map example is all constant. It has 3 keywords and a string. The second map example has an invocation as one of the values. And so whether the arguments to a map constructor are constant or they're dynamic, they're still emitted the same way. We'll come back to that later. All right, speaking of calls, invocations, how do those happen? If we're calling into Java, there's really 2 modes. Either the compiler knows precisely which method you're intending to call, in which case it's going to just put the arguments on the stack and apply any casts that are necessary, whether it's a boxing, unboxing, or a check cast, and then it's going to call one of the invocation instructions. You can also call constructors, but that's not on the slide. If the compiler doesn't know what the intended target was, it's going to do a slow path through a reflector. It's going to dispatch based on the name of the intended call. And so this is super slow. There's a compiler flag that'll warn when this is happening. I usually flip that on and knock out all the reflective calls. There's a few linters that also provide some feedback on what you're doing. Okay, so that's calling within Java. The fundamental calling interface in Clojure is called IFn. It's a little bit different than SAMs in Java, the single abstract methods, in that Clojure funds have arity polymorphism. So you can have different arities of the function do completely different implementations. Like in a Lisp, you can apply the function to collections of arguments, and you can also roll up arguments as they come into var args. Most data structures in Clojure have a useful default implementation for IFn. So as an example, keywords have an implementation of IFn where if you use a keyword as a call, it will serve as a lookup. So if I apply a keyword to a map, it digs into the map and grabs the value. So you can, if I'm mapping across a collection of maps, I can just pass a keyword directly, and I'll get a vector of the lookups back. It's super useful. All right, a little bit of code. There are 3 concrete examples of anonymous functions on the left, and then the IFn interface on the right. The IFn interface has 20 fixed arities, then it has an array collecting arity that's not on the slide, and it has a helper to apply arg lists into invocations. When a user types in a function. The compiler is going to generate an implementation of IFn that overrides all the matching arities. All the arguments are objects, and arities that you don't supply are going to just throw an arity exception in your face. Apply works through a mechanically generated argument spreader. It takes a list of arguments and it spreads them into invocation calls on the function interface. There's a similar adapter that exists for var args that's on the callee side, where it rolls up all the arguments into a list. So what are all those arglist equals null and util.ret1 calls? This is kind of interesting. This is one of the unique features of how Clojure maps to bytecode. It's called local variables clearing. I'm going to motivate it with an example in Java. So let's say you have a class called chain. It's like a linked list, and every time you call next, it makes a new link, and it points to it strongly from the existing link, and so it just sort of moves out to the right. And let's say we have a method that needs to iterate through this linked list, and it's trying to find something that's very far down the list. If the front of the list, the initial element, remains strongly reachable in a local variable, then a lot of other objects are now still reachable, and so they can't get garbage collected. So what we have to do is clear the local variables of references after the very last point that they're used. So if you're pushing an argument onto the stack from a local variable, you're going to push the argument and then go clear the local variable and proceed along your merry way. And so we do this because we have iteration over very large data structures, we have lazily realized lists, and it's important that if you're calling functions and passing lazily realized lists to helper functions, it's important that the original caller doesn't retain a reference to like the head of a list that will prevent GC from happening. So how does that look in Clojure bytecode? This is a named function that we're looking at. Previous functions have all been anonymous, but this one has a name, namespace doc. It takes one argument, n space, and it calls associate on it, assoc. Assoc is the immutable version of map put. So it takes a map, a key, and a value. And so what we see here in the bolded section in the bytecode is after the very last time we need that n space variable, we're going to clear the reference in the local slot number 1. And so we're going to push the 3 arguments to assoc on the stack, and the compiler keeps track of when the last instance of a local variable was used, and that's the bolded part at the top. And right after that point, it'll issue all those clears. All right, keen-eyed readers might notice a bunch of these invoke statics. What's with that? I thought everything goes through the IFn interface. Well, Clojure changed a few years ago to use a style of linkage where invocations to well-known named functions will directly call static methods in some cases, rather than dispatching through the IFn interface. So the bottom method that you see on the screen is the IFn implementation. It just delegates to the static method, but callers who call this function in some cases might not call through the interface. It might just call invoke static direct. So this direct linking style is used in the Clojure jar distribution itself. It's used for the core libraries. User space code is not typically direct linked because direct linking has a cost. It can't be reloaded at runtime. So notice the calls in the top function to Clojure/core methods. You can't do anything about those. You'd have to invent something to be able to reload that. So direct linking was a trade-off of dynamicity for performance. This is what calls look like when they're not direct linked. I've put in bold 5 bytecodes that represent a single invocation. So what we're going to do is we're going to get a var. A var is like a named box for a function. We're going to put that on the stack. We're going to dump the contents of the box on the stack. We will cast it to IFn, and then we'll load the argument, and we'll call through that argument. I've omitted local variable clearing here, but that's also in play. So the question is, can we have the performance of the direct linking style going through static methods, but also retain the dynamicity that Clojure users expect? Well, yes. We have Java language invoke, we have method handles, we have switch points, we have relinking call sites. Clojure predates all of this stuff, so the calling styles do not use any of those features. There's not a single invoke dynamic in all of Clojure. And so those static var boxes need to get into static fields somehow. And so in the class initializer, that's where they get populated. This is the implementation of a function, and it has to populate 3 different constants in the static fields. So can we do better? Sure, we could use condy and indy to do all the loads. We could do all the calls dynamically, and if we do it like this, then the class initializer becomes empty. There's nothing to do in it, so we can just load this. So that's interesting. But could locals clearing be done by the JVM itself? It has access to all the same liveness information about the local variables. It's a facility that the JVM could provide, in competition with n number of other facilities that the JVM could provide. So that's invocations. Sometimes functions need to close over variables. These are stored in instance fields on the function implementations. Local variables clearing needs to also clear the reference to this object in the first local variable slot, so that anything that you close over also isn't accidentally retained. So that's a very simple example of a closure, something that takes a database and it returns a function that looks up some sort of session ID in a database. It closes over the database argument. All right. There is a different style of invocation in Clojure, another facility called protocols. And you can think of protocols as interfaces that can be extended upon things that you own and also things that you do not control, like string or some message digest or some client library. So this is sort of a bag of methods, kind of like function invocations, but they can be slung onto different things that are in the environment. So here's an example of a protocol. So this is a protocol. It has a name, blob store. It has 2 methods, put and get. Protocols dispatch on the first argument. So the store argument is what any call site is going to dispatch on the value of whatever is passed in for store. So here is an implementation. This is an anonymous implementation of a blob store protocol. It uses an atomic reference to remember state, but essentially this memory store function returns an implementation of a blob store, an anonymous implementation, kind of like an inner class, pretty meat and potatoes. Another example is protocols. Protocols is a reduce protocol. If I wanted to reduce over some sort of target, providing a reducing function and initial value, I can extend that protocol to things I don't control, like I can reduce over a result set in the Java SQL package. I don't know what the semantics for reducing over a result set would be. There are probably too many semantics, but anyway, that's how you would use it. This is mostly a pedagogic example. Clojure already has a protocol for reduction that doesn't look like this, but this is sort of simplified. How do protocols work under the hood? They're like interfaces because there actually is an interface that gets generated under the hood. There's a backing interface. If the target of a protocol invocation implements that backing interface, it's going to call right through the interface. It's going to put the target, the arguments, and just call the interface method. Otherwise, the target is of a class that doesn't implement that backing interface, like string, like result set, and we're going to have to look up the implementation in some sort of table. Clojure uses a 2-level table. There's like a perfect hash map in that's small, and if it can't construct a perfect hash map, it will go through a persistent map. But as new targets are discovered, the perfect hash map is updated if possible, and the call sites relink. I say relink, it's not actually relinking any call sites, but it is changing the value of caches that are in static fields. One recent change, maybe a year ago, is that protocols got a third way of supplying an implementation, and that's through metadata on a data structure. And so in the purple, there's an ordinary map, has two keys, an algorithm, and a private key. Private key is some opaque implementation class. The map also has metadata, and you can think of metadata as a sidecar map that accompanies a certain data structure. The map isn't used for anything like equality, for lookup. That still goes through the main map. But now you can add implementations for things in the metadata directly, and protocol call sites are now sensitive to calling through metadata, as if the other mechanisms of dispatch don't succeed first. So this is really interesting. You can have different instances, different data structures that carry around protocol implementations, and users are none the wiser because metadata doesn't generally print into the REPL, which is nice. So this is one single protocol invocation in the bytecode. It's kind of a lot of bytecode. The target of the protocol invoke is in local variable 2. The args are in 0 and 1. But you can see in the bolded sections, there's the two primary methods of dispatching the protocol. One's calling through the interface, and one's calling through a lookup table that finds a function. I've also elided locals clearing from the example, so it's slightly longer. There's another branch in the bytecode that has an inline cache with the last seen class, and that helps skip over the backing interface check. All of this predates invoke dynamic, so you can easily see how, if you were using method handles, you can construct a couple guard with tests and achieve the same results and have one bytecode. So that's pretty cool. So let's look at data structures. I'll breeze through these because there have actually been talks at this conference about hash array mapped trees. This is the workhorse data structure. Both vectors and maps use this. Most languages with immutable data structures use some variant of this data structure, but the basic trick is that you take a 32-bit index and you split it into 5-byte segments, and each of those 5 bits tell you how to index down the tree. And so each 5 bits is responsible for branching up to 32, a branching factor of 32. The way vectors use it is the 32 bits are just the index into the vector. The way hash maps use this is that the hash of the key becomes the index, and so you just turn it sideways and sort of navigate through. We tried size specialization for low cardinality vectors, but that caused a bunch of issues with monomorphic sites suddenly not monomorphic anymore. All right, I'm going to skip over that, but there's a namespace mechanism in Clojure. Usually functions are anonymous, but humans need stable names in a program. So there's a way to register names. There's a collection of namespaces, and each namespace has a collection of vars in it, and vars are just, they're boxes with a volatile state in them. Usually the volatile state contains a function, but it doesn't have to. There's a fun fact in that the vars implement the IFn interface directly, kind of how in Java.lang invoke you have dynamic invokers on call sites so that you can always invoke the latest value within the call site. That's pretty much the same mechanism for vars. They implement they implement the function interface by delegating the function interface to whatever's in the box. Loading is pretty straightforward in Clojure. It's going to sequentially evaluate all the expressions in a file one by one. Most of the expressions involve constructing a var, instantiating a function, binding that function into the var, attaching metadata to the var where there is metadata. There's always metadata because you have line and file numbers and stuff like that. Loading a file might execute top-level side effects, too. We'll look at that later. So what are the challenges that we face? Like Java, we have a commitment to compatibility, which serves as a constraint on the design. It serves as an ongoing challenge to be compatible with the Java platform as it moves forward. Interop and reflection are particular challenges. Now that we have modules, the compiler has to figure out what methods to link to, and that's not trivial. There's not really a great API to figure out what to link to that's sensitive to bridges and visibility and all those things, those little details. So we have to re-implement a lot of that logic and stay abreast of that logic. So that's not great. Also, when we have value types and we have generic specialization in the coming future, we're going to have to play well with that. And I'm not sure what that looks like because the story isn't clear yet. So we shall see. The perennial thorn in the side for users, I think a lot of JVM languages get this, is load time. But load time is important because now we have function as a service platforms, and your load time translates into costs. That's pretty direct. And so if you're using some metered service like AWS Lambda, you're going to be charged for all the time that your Clojure Lambda spends initializing. But if you're using a scale to zero system like that you're always going to incur some sort of latency hit to ramp up and to scale up. But so these have load time's important to all these new platforms. I actually heard of this platform a couple weeks ago called Dark, where they claim to deploy to a cluster of machines in 50 milliseconds, which is kind of interesting. And if you took that as a design constraint, you would design your systems in a very different way. But I think this is going to become an ongoing tension with usage of Clojure. And so what are the reasons for long load times? The big one's gluttony. Developers are, just parsimony is a lost art. We use Java XML bind data type converter to do base 64 encoding and date formatting, even though there's better options. And we still find that a lot, even though the platform has official APIs to do that. Sometimes you might have long load times because you don't have an expressive API. Imperative builders are a lot of code to load, as opposed to plain data structures, which is pretty much the constructor to every subsystem in Clojure takes a map. There's no builders to figure out what to call. And part of the reason for long load times is the load semantics are form at a time. So if I load a whole namespace worth of files, worth of forms, it's going to sequentially evaluate all of them, and that's just what the semantics are. And so if somebody starts a thread pool on the loading thread, you're out of luck. So what do people do to mitigate load time? People are looking a lot to Graal native image, which is really nice, but it has a lot of restrictions that you might not meet. And if we put invoke dynamic in a call site, that it's possible that you can't compile with Graal native image anymore. And so Graal native image and tools like it are fundamentally they're closed world assumptions. And a Lisp with eval is it's open world, and Java's an open world assumption too. You could argue that dynamicity is the original superpower on the JVM. So I think this is an open problem. I've linked to a post from John Rose here. I think it's an open problem for the JVM. This post is called The Great Startup Problem, and it talks about startup and warm-up. It's a really good read. So what can we do to alleviate some of the loading costs? Constant dynamic allows us to put the class initializers on a diet and delay resolution of things until they're used in a function body. Invoke dynamic's the same thing. You pay the cost when the instruction's encountered. So that's great. I found that I tried using condy in run once code that will never become warm, and that was not a great idea because you're going to pay the bootstrap method linking costs. And so run once code includes when you compile a namespace, it creates a loading class, and that's only ever run once. So there's no point in putting condy or indy in there. It would be interesting to expose condy or indy as a special form in the compiler that would be inherently understood, but that raises a lot of questions about how do you encode constants that are passed to the bootstrap method. Sometimes you can pass strings, stuff like that, but now you can pass constants that were generated by condy, and so you can have recursive condys. That's really cool, but it still raises the question of how do you represent structures in that style. So let's look at an example of why we might need to encode constants, complex constants in an indy. So here we have a function called notice error. It takes a couple arguments and it fires a map to a dispatcher. If you look at the map closely, you'll notice that 3 of the 4 elements in the map are totally constant, but the only dynamic argument is an exception. And so wouldn't it be nice if that was the bytecode that we had? We'd load the 2 arguments, we construct the map, and we issue the call, and we return. That would be the ideal. But how do you express those 3 constants in the bootstrap arguments to an invoke dynamic? So you would have to encode the tokens themselves and some sort of steering on how to assemble the final data structure from the combination of the dynamic arguments and the static arguments. And so, you can think of a lot of different ways to do that. The stupidest way to do that would be to call Lisp read on a printed data structure. That works. I think Remy prototyped that a couple months ago. There are other ways you can make your own bytecode format inside some base 64 string. I don't know. You can go fancy. So looking to the future, this is not a promise, but the trends in Clojure. We got Git dependencies recently, so you can have your projects can refer to Git SHAs as their dependencies because there's nothing to compile. Everything's loaded at runtime. And it would be nice if libraries can go even smaller and you can have function level dependencies. To do that effectively, you might need to have a database for all of the code, the functions. You might need to reify that in some sort of way. But the real big challenge is helping programmers do their work across time. We looked at the spec system at the beginning of the talk, but spec is about compatibility. Is it possible to write predicates and evolve those predicates and determine, is there an algebra of, is this a compatible change across the program? Those are really interesting directions for Clojure, for Clojure.spec. For programming in general, I think coding across time is probably one of the big unsolved problems. So we can also map our bytecodes slightly differently, mapping our constructs into the bytecodes. I think we should look at the open-coded call sites like protocols and see if we can make improvements there. We could also look at different loading strategies for namespaces. Right now, we construct concrete implementations of IFN, but it would be cool if we can have a IFn that was a proxy to a bag of method handles. That would be cool, but it still requires us to maintain all the compatibility that we have with existing code. So, other things, Looming, Project Loom in a minute, but we have a library called core async, which essentially does it's a fiber system. It does the whole state machine shredding dance that a lot of fiber systems do. It does that in a macro. It's a Clojure macro. It's a totally user space thing, and it shreds a lexical region of code into like coroutines, and so it has like a little mini compiler within the macro. It's pretty neat, but it'd be nice to not need that because that's a second compiler that needs to maintain all the semantics with the first compiler. So nobody wants to do that. So it'd be nice to see what's happening with Loom and to see if we can implement the same constructs that this async library has, but on top of a different foundation. And finally, the ramifications of value types is super interesting, and I'm keeping an eye on this as this evolves. That might have huge ramifications. It might not have huge ramifications, but I would love to be poised to take advantage of it, whether it's in the implementation of Clojure and inside data structures, or if it's more exposed to the user. That would be interesting too. But with that, I think there's a few minutes for questions, and that's all I have.